and thanks for joining me for another little chemistry tale. Today we're going to apply the concept of the mole to a solution. Now, a solution in general is any homogeneous mixture, but we're going to be talking in particular about aqueous solutions. And the most common way to describe that mixture is via molarity. So the mole part tells you it has something to do with moles. Okay, and so it is the moles of solute, and this is key, for liter of the whole solution. So that's going to include any changes in volume that the solute brings. It's going to include both the solute and the solvent. Now, to make this, you would use a volumetric flask, typically. If you didn't need very much accuracy on this, then you could use a graduated cylinder. But usually you would use a volumetric flask, and here's how I would do it. I would take and add some water, some DI water. We would never use tap water, DI water, and then I would add my solute to that, whether that solute's added via a pipette, a graduated cylinder, or the mass of a solute. And so one, you're going to half fill with water, or even a quarter or a third, just a portion filled with water. What that does is it leaves you space so you can stir and mix effectively. 2, I would add my solute. And then 3, I would mix. And you could use, just grab the top of it and swirl it really well. Or you could use a stir bar and a magnetic plate to make that stir bar go round and round, which is lots of fun. And then what you want to do is you want to very carefully add water, okay, until the bottom of the meniscus is on the line. So you see that line there? You would want the bottom of the meniscus on that line. Now, if you saw like 8 volumetric flasks lined up, they're not going to have the line at the same place because each volumetric flask is calibrated. It's blown glass, and then they calibrate it to hold an exact volume. And so you have 1,000, milliliter, 2,000 milliliter, 500 milliliter, 250 milliliter, 100, 50, 25, 10. I mean, they're very set volumes, and they're very, very precise. Most of them are going to be within plus or minus 0.01 milliliter. So these are very accurate, glassware for analytical glassware for making solutions. Okay, now, finally, after you add water, you want to cap and mix it again. So you want to cap it off and mix. Now, it is possible. There are times that a mixture could be endothermic, meaning it got colder because it sucked in heat from the environment, or exothermic, which means it released heat into the environment and got hotter. So what you would need to do, meant to grab the pen there. What you would need to do is right in between here, you may need to cool it, or allow it to get to room temperature before you continued adding water to the bottom of the meniscus. But that gives you a general idea of how you would make these. So now let's do a couple of calculations. You may want to go molar mass to moles using molar mass and do these as a 2-step problem. Or this formula combines the molarity formula and molar mass is equal to mass over moles. So that formula combines those two formulas. Okay, so our givens are a volume equal to 1.5, a molarity equal to 1.500 molar solution. Moles are equal to 2.3 times 10 to the minus 2. And it says question mark liters. What is our volume? So remember, you want to next check your units, and my units are okay there. Since we're dealing with moles, I'm going to use the simplest form. Moles per liter of my SOL apostrophe N is for solution. And I like to solve my literal equation before I plug in. So you can plug in and then do the algebra. I just like to do my cross multiplying this way first. I feel like it's a little less writing. So I just cross multiplied to solve for my liters alone. And I would get 2.3 times 10 to the minus 2 moles divided by 1.500 molar. And assuming I've done all of my algebra correctly, I would have 1.5 times 10 to the negative 2 liters. Okay? And maybe it might ask you to convert that to milliliters. Hard to say. Okay? Now, let's take a look at this next one. This would be a really common one that I would have to do if I was, setting up an experiment for you. So how many grams of silver nitrate? So it's question mark grams, my givens. I have a volume equal to 250.00 milliliters. And I have a molarity equal to 0.02450. Okay, so those are my givens. I want to check my units. Now, milliliters are not okay. We need to use liters. So I'm going to convert those milliliters to liters. Now, I would not be a decimal shifter if I were you. You'll often move it the wrong way. So, plus you might lose points for showing work. All work must be shown in order to get any credit. And so you want to make sure that you show that work so that it's clear if there is a mistake, it's clear that it's a minor math mistake as opposed to a conceptual error. Minor math is usually a smaller ding than a conceptual error would be. Okay? And now I'm going to use my equation. You could certainly use this one, solve for moles, and then convert moles to mass using molar mass. I tend to like to use this big, wrote that down wrong, 2450 molar is equal to mass. Silver nitrate's molar mass is 169.87 over my volume of 0.250 liters. This is showing the one-step problem. So if you did it this way, step 1 can calculate moles, step 2 convert moles to mass using molar mass, or you can use this entire formula. And I ended up with a mass of 1.040 grams of silver nitrate if I wanted to make that solution. So, thanks for joining me. I really appreciate your time. Hope this helps. Good luck.